السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. Inshallah, today we'll continue talking about naive Bayes. Inshallah, we'll finish it, hopefully. And if we have time, we will start talk about logistic regression, which is the last piece in this session before we, inshallah, jump into the neural network session. Last lecture, we went through the main concept of naive Bayes model. I think we saw example, but we didn't have something hands-on exercise that we solved. So I thought that we will start with this example. Let's say that we have given this training set, and we want to learn a naive Bayes model out of it. So please take a piece of paper and try to learn a model from that, and tell me how we can do that. So, what should we do first? Yes, so the probability of the classes first, right? So we need to calculate probability of y equals 0 and probability of y equals 1. Okay. So what is the probability of y equals 0? 4 over 10. So 1, 2, 3, 4. Yeah, so that's 4 over 10. And probability of y equals 1? 6 over 10. That's easy, right? Then, so we'll have to fill the big table, right? So what should be in that table? The conditional probabilities, right? So so we'll have the table like that. We have xi, which is specific feature, and y, and probability of xi given y, right? So let's do for x1 first. How many possible values are? 3, which are a, b, and c. So when x1 is a and y is 0, y is 0, then we need to compute the probability of x1 equals a given y equals 0. And then we also need to compute when x1 equals a and y equals 1, right? And when x1 equals b, y equals 0, when x1 equals b, y equals 1, then c 0, c 1, then x2 equals 2, 0, 2, 1, false, 0, false, 1, and then x3, and so on, right? So let's try one of them. Let's try this one. So when x1 equals b and y equals 1, we want to compute probability of x1 equals b given y equals 1. What would be that? 2 over 6. How did you know that? How did you get that? 6 cannot be a probability, right? Yes, so that's the count of how many times y is equal 1, which is 6, right? How many of them when x1 equals b? This is 1, this is 2, right? So it's 2 over 6. Right. Let's do this one, the first one. When x1 equals a and y equals 0, what is the probability? What is the conditional probability? Why is it 1? Okay, which is this one. So it will be just 1? 1 over 4. Very good. Okay, 1 over 4. This is 4, not 9. Okay, Is that clear? Any question about this? So we should compute all of this table, right? All of these probabilities. How many rows we will have in this table? Is there a systematic way to know how many rows? The combinations of what? Who said combinations? Combinations of what?
Like we do the number of parameters and then combination of two.
So can you tell me 3 times 4 times 5 times 2? Can you tell me something like that? This is how I'm expecting you to compute it. Sophia?
So for x1, it will be 3 features times 2.
Why is it times 2?
Each feature is done twice for y equals 0, y equals 1.
Very good. Plus or times? Plus. Yeah, so for the first feature, we have 6 rows. Why is that? Because we have 3 values. And for each, we need to compute the conditional probability for each class. Okay, so that's for feature 1, feature 2. 2 times 2. Then 3 times 2, because feature 3 has 3 possible values. Okay, so this is 6 plus 4, 10 plus 6, 16. Okay. Of course, you could have done it by the number of possible values of all features times 2. That would be 16. Okay, any question about this? Type. Where is the trained model? That's the table. The table is the trained model. Is the trained naive Bayes model. Okay, all the values that we computed are the parameters of the model. Okay, all of them are the probabilities. Okay, whether they are conditional probabilities or the probabilities of the classes. How many probabilities overall that we compute here? 18. 16 the conditional ones and 2 for the classes, right? So these are the parameters of the model. Now we learn the model, right? Any question about how to compute these probabilities or this model? No questions? Right. Now can I compute the conditional probability of any given example? Yani, can I predict the label for any given example? Or only the examples that we see in the training set? Any. But let's do it step by step. Can we do it for unseen example? An example that I didn't see before? Can I compute the probability? And can I compute probability of y given x for any for unseen example that's not in the training set? Can we do that? How? Yeah, so that we saw that last time, right? We expanded last time. Can you remind me how we expanded? Probability of y times of x given y, right? In general, that's Bayes rule divided by probability of x. And then we had 2 assumptions. I mean 2 steps. We ignored p of x, right? Because it will be repeated for every class. So it's just it's like dividing by a constant. It will not change the prediction. Yes.
If you say it's unseen data, how do we know its distribution?
We will assume it's from the same distribution. Okay, we will assume that it's from the same distribution. Otherwise, we will not be able to. Otherwise, we can of course predict the label, but it won't be accurate. Okay, so we'll assume that if we can compute the features of this example, the same way we got the features for the training examples, then we can predict the label. Okay, so we can get rid of this p of x, right? Which means that this is an approximation. It's not a probability now. It's like a score. Type. what did we do with P of X given Y? We ignore it. What happens if we ignore it? Okay, so we'll not ignore it, of course. We will expand it. Okay, if we expand it exactly, we'll have to use the chain rule, but we also had the naive independence assumption, right? Yes. So that's so P of X given Y will be expanded to what? In our case, it will be probability of. Now, in our case, well, tell me in our case. So probability of x1, that's the first feature, given y times probability of x2 given y times probability of x3 given y. Right? And that's how we can compute the score for this class, for this example. Type. This example has to be unseen. And for unseen, we can compute it, right? The foreseen example, can we compute it? So we can compute for any example. Type. Let's assume that we have the trained model, and now we want to predict the label for this example. What should we do? Compute the probabilities, right? Type. Can someone tell me what are the steps? What is the first step? Nama? Yes, probability of y equals 0. Why is it y equals 0? Fine. Let's start from scratch. Okay. What should we do? What is the major step that we need to do here? Now we are given an example. Let's say that we have this big table here. Okay. We have all the probabilities here. Khalas? We trained the model. That's the model. Okay, we trained it already. Khalas, we computed all the probabilities in that table. Now I want to predict the label for this specific example. Or any example. Let's say I want to predict the label for any example. What is the step, Aya? Why we need to do that? Why? Of what? No, that's what I'm looking for. Very good. So we need to compute probability of that the class is 1 given x, and also probability that the class is 0 given x, right? We need to compute these two because we have only 2 classes. If we have 3 classes, then we have to have 3 probabilities. And if we do that, then what will be the prediction? The one that has the maximum value. Okay? Type. Notice here, of course, that this is like the opposite of what we have learned, right? We learned the probability of the feature given the class, but then we need to infer or predict the probability that this is the class given the example now. Type. Now, how can we compute this? Of course, we'll compute an approximation or a score, right? So, what will be the expression here? P of y equals 1 times P of what is C? x1 equals C given y equals 1 times probability of x2 equals 2 given y equals 1 times probability of x3 equals 0. Very good. Given y equals 1. Right? Type. Do we have all of these values? Do you have this value in the model? This value. Do we have this? We have this. Do we have this? We have all of these already computed in the model, so we can compute that score. Okay. Similarly, we can compute the score for the other class. What will be the difference? Yeah, so it's exactly the same except that y will be equal 0 in every factor. Okay, so we'll have 0 here, 0 here, 0 here, 0 here. Type. Why don't we say just 1 minus whatever the number that we will have here? Yeah, because these are not the exact probabilities. Okay, so don't fall into this. Okay. Type. We got a number here. We got, let's say we got A here, we got B here. What should we predict? So we computed this. We can compute it from the model, right? We got a number. Does it have to be less than 1? It will be less than 1. Okay, it will be less than 1. Okay, but it's not an exact probability. So we got a number here. We got a number here. What should we do next? What do you mean by predicting the label? What's the meaning of this question? Now this is the meaning of prediction. It's to say which class the model thinks this example belongs to. The greatest one. So B is greatest. So what should be the predicted label? Not B. Not the probability of Y. 0. Okay. The prediction is a label. Is one of the classes. Right? So it's not a probability, it's not a score. It's one of the classes. So here, if B is greater than A, then of course we will predict 0. Otherwise, we'll predict 1. We don't care about how to compute probability of X, really. We didn't model it. We didn't say how we can compute it. And we will not need to compute it. Okay? But, I mean, if we want to predict. But if you want to compute the confidence, because if we want to compute the confidence, then this has to be exact probabilities. Okay. So let's take an example here. Let's say that this value is 0.2, and this one is 0.3. Okay. Of course, they don't sum to 1, right? But the exact probability is sum to 1. We know that the exact value of this probability is 0.2 over something, right? And we know that this is 0.3 over something else, or the same thing? Same thing, which is the same probability, right? So this is 0.2 over A and 0.3 over A. And we know also that these two probabilities sum to 1. So 0.2 over A plus 0.3 over A equals to 1. What will we get? Can we get A now or not? We can, of course. So this is 0.5 over A equals 1. So A equals 0.5, which is the sum of these two. Okay. So the actual probabilities are 0.2 over 0.5 and 0.3 over 0.5. Okay. Of course, we don't need to solve this equation to do that. This is called normalization. We just divide by the sum of them. If we divide by the sum of them, then we get the exact probabilities. Okay. But you have to get both. You have to get both to do it. Okay. Type, let me ask you a quick question now. This is the training set, right? And we had a model out of this training set. Type, what if I need to measure the generalizability of that model? How good this model actually is? In other words, how can we test that model? Who is talking? Using test data. Okay, where's the test data here? We don't have it here, right? But we assume that if we want to do that, then of course the test set is separate, right? Remember the cardinal rule, right? So the test set and the training set should not overlap, of course, and the test set should not be seen. So in this case, we'll have to have a test set, and we need to test the model on this test set. But the test set is labeled or not? Is labeled, right? Type. If the test set is labeled, then it's seen, right? But we are saying that we should test the model on unseen data, right? Type. You all agree that the test set will be labeled, right? Type. How come it's labeled, and at the same time we will test on it as if it's unseen? And it is seen, right? Labeled means it's seen, right? Someone labeled them, right? Manually, right? So we have the actual labels for these, so they are seen. They are not seen. How are they labeled if they are not seen?
We have the data that we want to train the model.
Okay. Okay.
That we take specific, we split them to take the test set.
Okay, but the test set is labeled, right?
Yeah, labeled.
So it's seen,
But we
right?
separate them.
Huh?
We separate them.
I know we separated them, but they are seen, right?
No, we train the model on the.
How did we label them if they are not seen? We labeled them, right?
No, who labeled them?
Who labeled them? Okay, who labeled them? Very good. That's the question. You are asking me, or you are? I'm asking. You are asking me. Okay. Who labeled them? مش عارف حقيقة. Okay. Who labeled them?
If we're gonna use them to test, okay?
طيب يعني.
We just don't give the labels to the machine. We give the data itself.
That's the idea. Okay. So they are seen by some humans, of course, who labeled them. Okay. And they must not be us, of course. Okay. So someone, that's the answer to your question. Someone labeled them. Okay, for us, but we don't see the labels. Okay, so when we train our model, of course, the labels are not seen. I mean, all of these examples, which are in the test set, are not seen to the trained model. Okay, طيب. The trained model will be used to predict the labels for every example in the test set, right? Why do you need the labels? If the model will actually label them. Yes, to compare, right? To compare. Okay? Just a revision of what we have seen in the course so far. Okay, good. Any questions? Right, this is the, I think the slide that we skipped last time. I told you that after training, I think it will be clear. This is now, I think, should be very clear. That's the pseudocode for training. So given the training data, for every value of the class label, we need to estimate the probability of the class. And then for each feature, for each value of this feature, we need to estimate the conditional probability. So this is the code for, or pseudocode for computing all the probabilities in the model. And this is how this probability will be computed, and this is how that probability will be computed. And this is exactly what we did in the previous slide. Okay? Any questions about training or testing with naive Bayes? Okay, one last slide. Now imagine that in let's get back to the example. Let's just assume for now that C didn't appear when y equals 1. Yani here I think C appeared once here and once here, right? Let's say that it didn't appear with 1. Yani let's say that all of these are zeros. What will happen with with this now? So this probability will be 0, right? And thus the entire probability will be 0, right? Because 0 times anything is 0. Type. Is that good or bad? Why is it bad? It's 0. It didn't appear, right? So this feature didn't appear with the class. Then the probability of this feature given the class is 0. Fine, but this feature didn't. So if it appeared in the example, then this example will not happen. So the estimated probability here will be 0. Good or bad? Still bad, but we don't know why. Yes. So can it happen that this didn't appear in the training set, but it can appear in the test set? It can happen. Why? Because they are separate, right? Can it happen that it's neither in the training set nor the test set, but it exists in reality? It can happen, right? How come? Why? Why didn't it appear if it exists in reality? Why it didn't appear in the data that we have? Huh? Like what? Bad data representation. Okay. What's the problem with that? Why is it bad data representation? That's the point. Okay, that's the point. That the data that we have, the labeled data that we have, is a very, very small sample, usually. It's a very, very small sample of what exists in reality. Okay? So, not everything will be represented. We should expect that. But of course, if it didn't appear, as you see, it will be a problem, right? Because we will assume that it's 0. It will never happen. But actually, it will happen, or it can happen. Okay.
So we say that the data set is small. That's why we have probability of 0.
Data set is always small relative to what exists in reality. Usually this is the case. Okay. So it's just a sample of what exists. So something that didn't appear at all in the labeled data that we have doesn't mean that it will not appear in reality. Okay. So if we use that model, then with that feature didn't co-occur or didn't happen with specific class, will lead to 0, which is bad. I think now you understand why is it bad, right? Right? Right. Question.
So when can we say it's unlikely to happen? Like it will not happen? Or we can't say that?
I don't think we can say that. Actually, we can, and that's the solution. We can assume that everything will will happen even with small probability. Okay, and that's actually the solution. So if we get back to the slide, so what happens if a feature value didn't co-occur with a class? We'll get 0 probability. Okay, so of course that will be like a short circuit. And if one of the probabilities is 0, then the entire probability or the entire score will be 0. So how can we solve this? This type of problems, the solution is called smoothing. What do you mean by smoothing? The problem here is that we have, let's say that all of these features and values are events that can happen in reality. Some events, we saw them, we observed them in the training data, right? So we can compute probabilities for them. Some we didn't observe in the training data. So the computed probabilities will be, for them, will be 0, right? So it's like that some events will have probabilities. See that this is the event, and this is the value of the probability of that event. Okay. Some of them will have some probabilities, and some of them will have small probabilities. Some of them will be 0. So many will be 0 because they didn't appear in the training data, right? So smoothing tells us that every event should have a probability of being observed. No event should have 0 probability. So instead of this distribution of probabilities, we should smooth it so that all the events have some probabilities. Okay, so these probabilities should not be 0. It should be very small probability. But to give these events these probabilities, we should take some of the probability space from the others. That's why it's called smoothing. Okay, it's like redistribution of the probabilities. We take some part of the probabilities of the observed events and give it to the unobserved events. Okay, and one way of doing smoothing, so smoothing is adjusting each probability by a small value. One type or one method of smoothing called add-one smoothing. What do you mean by add-one smoothing? We will assume that every possible event happened at least once. So we will add 1 to all counts that we have. Okay, so for example, a feature appeared with a specific class 3 times. Instead of taking 3 as the count, we will add 1 to it. So it will be 4. Type. What if it didn't occur at all? It will be 0 plus 1. Okay, so we will add 1 to every possible combination of the features with the classes. Okay, so for example, let's get back to the table here. Let's say that we want to compute P of B given 0. What is this probability now without smoothing? 2 over 4. 2 over 4. Right? Because 0 appeared 4 times. 2 of them we had B. Right? Right. With smoothing, this should be so the numerator first. The numerator will be 2 plus 1. Right? Because we will add 1 to the frequency or the appearance number of occurrences of that feature. So it will be 2 plus 1. Now what should we do with the denominator? Remember that every feature value, we will add 1 to it with that class. Okay, so the denominator should be 4 plus 1 for every feature value. How many feature values we have here for x1? 3. So it will be 4 plus 3. It's as if we add 1 more B, 1 more C, 1 more A. Okay, and then compute the probabilities as we did before. Okay, so it will be 2 plus 1. What is this one? This is because of the smoothing. And 3 because we have 1 for each possible value. Okay, so in this case it will be 3 over 7, not 2 over 4. Anything that was 0, it won't be 0, right? Because the numerator will be 0 plus 1 over non-zero value, then it will not be 0. Now, if you compute P of A given 0 and P of C given 0, this way, and you add them, you will have to get 1. If you didn't add these 3, you will not get 1. You'll get maybe more than 1 because you added to the counts, but you didn't add to the total. Okay? So, this is another check that you should have. Did you get the idea here? So, we'll add 1 to every possible value of the features per class. Yani, when we do it for P of whatever value given, we're talking about specific feature, okay? So for every feature, that has to be done for every feature separately. So probability of A given 1 and probability of A given B given 1, probability of C given 1. All of these are belong to the same probability distribution. So the sum of them has to be 1. So we'll add 1 to the numerator. It's add 1, yes. Okay. And how about the denominator? 3, because we added, it's just these ones, right? So I will have to add these ones. So we'll add 3 here, add 3 here, add 3 here. How about x2? We'll add only 2 because we have 2 possible values. We have 2 possible values, so we add 1 for each, it will be 2. Okay? That's add 1 smoothing. Of course, there are other types of smoothing. There is another type called Laplace smoothing, when you add small value to each feature value. But we'll just stick to add 1 smoothing as an example of the concept for this class. Any questions? So do you think you can now, given label data, you can train an naive-Bayes model without smoothing and with smoothing, with add 1 smoothing? Any questions? So with that, we are done with naive-Bayes model.